Hi everyone. So this is the first video in the alkyne notes series. In this one, we're going to go over just a few quick details about alkynes and compare them to alkanes and alkenes. And then we're also going to go through two addition reactions, which are hydrohalogenation and then halogenation. So let's first start off with just comparing the alkanes to alkenes and alkynes. And so here I drew a skeletal notation of just a two carbon molecule that represents all of those. And so let's first add in those hydrogens. So I'll add them in red just so we can kind of see how many we have. And so for an alkane, we're going to add in three to both sides. In alkene, we're going to add in two. And then an alkyne, we only have one that we're adding in. And so if we were to compare the different details about the structure here, we can see that alkanes are going to be sp3 hybridized at each carbon because there's three bonded groups. Alkenes are going to be sp2 because there's only three groups at each carbon. And then an alkyne is going to be sp for each of those carbons because we only have two groups bonded to each carbon, which is the hydrogen and the other carbon. And so then we can enter or input the geometry of each of those carbons, which means that each carbon will be tetrahedral for the alkanes. We're going to have trigonal planar geometry for each carbon in the alkene. And then we're going to have linear geometry for the alkyne. And the fact that alkynes are linear is a very, very key part of their structure. It's going to affect a lot of different structures that you can get, and then also affect the reactivity of the molecule. And so if we were to think about each of those bonds, for the alkane, we only have sigma bonds because we have no double bonds or triple bond. And so an alkane is just one single sigma bond. An alkene is going to be a sigma bond plus one pi bond. And so we know that if we were to draw out the orbitals, we would have one that extends, it would look something like this, where we have that pi orbital that extends above and below that bond. For an alkyne, we end up having two pi bonds. So we have one sigma and two pi bonds. And so if we were to draw out those pi bonds, we would have one that extends above and below that sigma bond. And then we also have a second pi bond that is perpendicular. And it's a little bit hard to draw in two-dimensional representation, but basically it looks something like this, where that green pi bond would be that other perpendicular one to that blue one. And so as a result of that, those two bonds are very reactive. And so similar to alkenes, an alkyne can act as a nucleophile because it has that extra pair of electrons in that pi bond that can attack something else. And so we're going to see a lot of similarities between alkenes and alkynes for their reactivity. And both of them are going to serve as the nucleophile. Since we only have a sigma bond in an alkane, these are very seldomly, they're really not reactive. Sigma carbon-carbon bonds are one of the least reactive groups that we could potentially have. And so we don't really see reactions with alkanes in the same way that we do with alkenes or alkynes. In terms of reactivity, alkynes tend to be the most reactive, and we'll see why that's relevant for things like reductions in the upcoming videos. The last thing I want to point out about double bonds and compare them to alkynes is that we can end up having cyclic structures that contain both alkanes and alkenes. So for example, we could have cyclohexane where all of those are single bonds, and we can get the bonds to bend in a way where we could form a cyclic structure. Same thing with alkenes. We can get the 6-membered ring or 5-membered rings where we have an alkene in the ring. And that's because with the trigonal planar geometry, we actually kind of end up having a good geometry where we have the hydrogen and the other carbon bond within that ring. However, a key part of alkynes is that we actually can't get linear, or if we do have a triple bond within a ring, such as this, it tends to be not very stable because of the ring strain that forms. Um, and so this bond right here ends up having ring strain, or this entire structure ends up having ring strain because this structure is bent out of linear geometry. So alkynes want to have only, since they only have those two groups bonded to it and no hydrogens, in this case, these four atoms that are bonded here are being bent out of their optimal linear geometry. And so this ends up being not favored. And as a result of that, more reactive if you were to force the structure into this. And so we seldom see triple bonds within a ring system. All right, so let's move on to some reactions. And so for the first reactions we're going to go through hydrohalogenation and halogenation. And so the reason we're going through these first is because these are very, very similar to reactions that we've already seen with alkenes. We're going to see that basically it's the same reaction, but happening twice. But we're starting off with an alkyne instead of an alkene. And some of the key differences between alkenes and alkynes end up manifesting when we go through things like reduction or oxidation reactions. And so those will be in the upcoming chapters. But this should feel like a review of alkene reactions. So for this one, the first one, hydrohalogenation, we have two parts. We have hydro, then we have halogenation. And so what that means is that we're going to be adding a hydrogen and a halogen. And so in all the reagents that we have here, we have the halogen that's highlighted in blue, and we have the hydrogen or source of hydrogen highlighted in green. And so I'll start off with this molecule here where we just have a terminal alkyne here. And so for this one, I'll just use HCl as the example. And so for this, we'll assume that we have an excess of HCl or HBr or HI, meaning that we can have multiple of the HCl's react with the starting material. In general, these reactions are really, really hard to control. And so it's a little bit tricky to just get a single addition of each of these. And so in general, that's not really something that chemists would usually try to do, where they would try to stop the reaction with a single addition. But let's say that we have this. So as we recall from our previous chapter, we would get that the alkyne acts as the nucleophile on the hydrogen. And so we end up forming this intermediate here, where the hydrogen ends up getting added to the terminal carbon here. And we kind of, it's not quite a carbocation, but it's like a proxy structure that we can draw to represent the intermediate state here, where we end up getting that plus charge on that other carbon. And again, the state is not quite correct. Different textbooks will describe this intermediate state a little bit differently. But for the purpose of most orgo classes, this should be sufficient. And then the next step, we have that the chlorine attacks at the carbocation, or kind of carbocation, it's not quite that. And altogether, we end up adding a chlorine. And so what we can see is that that chlorine was added onto the more substituted carbon, and that's because that positive charge is more stable when it's internal and not on a terminal carbon. All right, and I'm going to make this a little bit smaller so we can see the next step. All right, so that's the first step. In the next step, we now have an alkene, and we have another copy of that HCl, where that alkene can add on or attack that hydrogen again. And we end up forming a true carbocation intermediate now. And that hydrogen that I just highlighted in green ends up getting added to that primary carbon on the end. And again, we're following those same rules that we did with the previous chapter, where the carbocation goes to the more stable position. We actually now have a chlorine there that's potentially contributing to the electron density within that region. And so we end up adding that the carbocation to the same carbon. Then in the next step, that chlorine can come in again, attack that positive charge, and we end up forming this structure here, where we have those two chlorines on the same carbon here. And one thing that I want to point out here is that the product that we get here has the chlorines on the same carbon. And so the term for this is geminal. And so we end up having a product where those two chlorines went to the exact same carbon, and that's the one that's going to be more substituted. And if we review the reaction, we can see that it's basically the same step twice, this step or these two steps followed by these two steps, exact same thing that's happening. We get attack at the hydrogen or nucleophilic attack at the hydrogen, and then the chlorine comes back in and forms that bond. All right, so that's going to be hydrohalogenation. The next one we're going to do is halogenation. And so within this reaction, we're adding 4 total halogen atoms, which can either be bromine, chlorine, and I'm also missing iodine there. So I'll add that in really quickly. But basically, we're just going to add all 4 to all 4 of those halogens to the molecule. So first, I'm going to start off with the same exact molecule. We'll start off with a bromine here. And as a review of what happens, we end up having that bridged halonium ion form in that first step. And similar to the previous chapter, some classes don't draw this out as the bridged halonium ion, but this is the more common representation of what that structure intermediate looks like. All right, then from here, we have attack at the more substituted position, kicks off that bromine and opens up that bridged halonium ion. And so now from that first step, we get addition of 2 bromines. And I'll highlight the bromines just so we can keep track of where they came from. That highlighted green one is the one that was initially on the bridge structure. And then I'll use blue to show the one that's coming in. And I'll highlight the starting Br2 just so we can keep track of what's going on there too. All right, next we can have the same exact copy of the same reaction where we form another bridged halonium ion. And if we look, this is going to be the exact same step as what we just did in that first step. And next we have another bromine come in and open it up from the more substituted position on that bridged halonium ion. And so now I'm running a little bit out of space here, so I'm going to shift all of this over. And so our final product ends up having those same 4 carbons that we started off with. And then we added in bromines at each of the carbons that we started off with. And then we also have that extra hydrogen that I'm not drawing in, but it's on that terminal carbon. And so here I'll just, for that last step, I'll highlight where each of those bromines came from to help kind of make sure that we know where everything's coming from. All right, and so once we highlight those, I think that will wrap up this video. And in the next one, we'll talk about reduction and oxidation reactions related to alkynes. And then a little bit later, I'm going to also post some practice problems for alkynes, which will be linked below.